First part of this is stuff we've already sort of talked about, but just a quick review, it's been a while. This stuff you should know from chemistry. We know the nucleus is where you're going to find the protons and the neutrons, and almost all the mass of the atom. And that we might call a proton or a neutron a nucleon, because they're in the nucleus. You know your atomic number. For some reason in physics they call it Z. And your mass number, for some reason they call it A. So atomic number always tells us what? Number of protons, and mass number always tells us protons plus neutrons. So carbon, for example, 6 protons, and 14 minus 6, 8 neutrons. Those are called nuclear symbols. Now remember, isotopes are like carbon 14 and carbon 12. What's the difference between those two? Numbers of neutrons. Straightforward stuff on that slide. Also remember that the mass of a proton and the mass of a neutron are essentially the same. Small difference, but the difference is not out until like the 27th place, so they're essentially the same. Sometimes we'll call that mass 1 AMU. The mass of a proton or a neutron. Also remember that what holds the nucleus together most is the strong nuclear force, which is mostly caused by what? This is the job of the neutrons, right? Because the protons want to do what to each other? Push apart. The strong nuclear force helps to hold the nucleus together. And remember that for small atoms, the number of protons and the number of neutrons are essentially the same, like right down here with the really small atoms. As you get bigger, this blue line represents the numbers if the protons and the neutrons stayed the same. So it's just like a straight line. But as the atoms get bigger, they don't. It takes more and more neutrons to hold it together. And that's why instead of being a straight line, we'll get more of a curve when we're looking at protons plotted against neutrons. All right, this binding energy stuff we talked a little bit about last time, but let's make sure we got it. When an atom is made, if you add up the mass of all the pieces add up to be a little bit more mass than the actual atom. Because when it's made, what happens to some of the mass? Yeah, it gets turned into what? Energy. And we can calculate that. One of the ways to calculate the amount of energy that's given off is to use Einstein's equation. E equals mc squared. Where m is what? Which mass? The amount of missing mass. The mass that seemed to just disappear, which it did disappear, turned into energy. And then c is the speed of light, squared. But that energy, that mass that just seems to be gone is called the mass defect. And it's proportional to what's called the binding energy, the energy that holds the atom together. 1 AMU of missing mass is equivalent to a whole lot of energy, 931.5 million electron volts. Bunch of energy. And like it says here, the greater the average binding, I should say energy, the more stable the nucleus. And what we see is that atoms around this size have the most binding energy per nucleon, per proton or neutron. So in nature, atoms that are bigger than that tend to fission. They tend to be radioactive. Fission means what? Split up to get closer to that size. And atoms that are a lot smaller than that, they tend to fuse to get closer to that size. Because that's stability. And that's just kind of like going to equilibrium if you're talking about diffusion in biology. That's where they want to be. That's the equilibrium state. Oops. Picture must have been hyperlinked. All right, the main thing though we want to concentrate on today and try to finish up today, radioactive decay. Decay is simply when what happens? The nucleus starts shooting out pieces. It starts falling apart. And it can shoot out different kinds of things. But when it shoots out those pieces, the atom transmutes. What does that mean? It changes from one element to a completely different element. Transmutation. For example, eventually all the uranium in the world will one day be what? Lead. Lead slowly transmutes. Uranium slowly changes to lead. That'll be a long, long time. We don't have to worry about it. It won't be in your lifetime. It'll be a long, long time away. You need to know these symbols for different kinds of particles involved in radiation. If you have a 1 and a 0 and an N, that's just a neutron. If you have a 1 and a 1, and either a capital H or a P, that's just a proton. 0 and -1, that's an electron. 4-2 and HE, or 4-2 and what's that funny symbol over there beside it? It's an alpha. It's an alpha particle. Notice that 0 and -1 can also be a beta particle. Or it could be 0 -1 beta. Because a beta particle is essentially an electron that's getting shot out of the nucleus really fast.
Are we going to have to know these in the test? Like from memory, or will there be choices?
You need to know these symbols. Yes. And we'll talk about positron in a minute. A positron, notice, looks like a beta particle in terms of symbols, except it's +1 instead of -1. We'll talk more about what that means in a second. All right, I think we talked about the first couple of kinds of decay last time. But let's start with alpha decay. In alpha decay, an unstable nucleus essentially starts shooting out particles that are essentially the nucleus of a helium atom. Shoot them out really fast with a lot of energy. But essentially they're the nucleus of a helium atom. And again, we might write it as 4-2 alpha or 4-2 HE. Depends on who wrote the question. This is called the nuclear equation. And the nice thing about these equations is that the numbers have to add up on both sides. If this is 226 right here, all the mass numbers over here have to add up to be 226. If the atomic number over here is 88, these have to add up to be 88. So you might get a question something like this. Say you had americium, and let's say it's 95 or 243, and I told you to write out the equation for the alpha decay of that element. Write out the equation for the alpha decay. Well, you know if it's doing alpha decay, it's 4-2 alpha. But you probably don't know right off the top of your head what the other thing is. But you know the numbers have to add up. If this is 243, this number over here has to be 239. If this is 95, this number over here has to be 93. And then you just look at the periodic table, and you see that element 93 is Neptunium. So it's pretty easy to write those equations. But that's alpha decay. If I was shooting alpha particles at you right now, would you be very concerned? It would depend on how many, but alpha particles are kind of big and massive, which means what? They can't go through very thick things. A thin layer of clothing would block them. Now you wouldn't want them in your lungs. You wouldn't want to be breathing them in like radioactive gases or something. But they're not going to be able to penetrate your clothing. Am I saying what? I think it fell apart a long time ago. Yeah, it's decaying. Let's just put it that way. All right, beta decay. I didn't even do the political statement there, Mark. Beta decay, another way. In beta decay, essentially, a neutron splits. And the neutron becomes what? Two things. A proton, a positive part, and a negative part, an electron. The proton stays in the nucleus, but the electron rather is shot out as a beta particle, shot out under high speeds with a lot of energy. So here's carbon-14. We all know it's radioactive. When it goes through beta decay, first of all, we know that's a beta particle. Remember, we also might write it as 0, -1, e. That. These numbers still have to add up, though. If this is 6, these two have to add up to be 6. And if this is 14, that's got to be 0, so that they add up. So let's say that we, I'm not even sure if this element does beta decay, but we'll just make up one. Let's say that we wanted to see the beta decay of Einsteinium. And I said, write out the equation for the beta decay of Einsteinium. Look it up in the table. Again, but you know it's beta decay. So you write your beta particle. If this is 99 and that's -1, this has to be 100. If this is 252 and that's 0, this has to be 252. And then you look at the periodic table, and element 100 is fermium. Okay. So again, remember in beta decay, essentially a neutron breaks apart. It leaves behind a proton that stays in the nucleus, and it shoots out the electron as a beta particle, high-speed particle. All right, another thing that can happen is called electron capture. And this is essentially when the nucleus captures a negatively charged particle. And notice that when it happens, essentially one of your protons becomes what? A neutron. Essentially we're converting a proton to a neutron by the addition of this negative charge. So this is like cobalt 57. It catches that electron, that high-speed electron, and it transmutes from cobalt to iron. What did we say this funny symbol over here was?
Neutrino.
It's a neutrino. It doesn't have charge, so most of the time, and I think typically in an AP Physics test, you would not even see this listed as one of the particles. Still learning about what neutrinos are. Still kind of theoretical in a lot of ways. Probably you're not even going to see that in the equation. Put it up there just in case you do. It's not going to affect the way the equation works, though. These numbers, 27 and -1, those have to add up to be whatever this element is. So 26. So let's do one more example. Let's say we had thorium, which is 90 and 232. And the question that I gave you is, show the nuclear equation for the electron capture of thorium-232. So if it's an electron capture equation, you know that you've got to show thorium-232 capturing an electron. Add up the numbers. 232 plus 0 is 232. 90 plus -1 is 89. You look in the table, and you find element 89, which is actinium. And like I said, typically you're probably not going to show that neutrino. If you want to tack it on there, that's fine. Either way would be okay. That's electron capture. And then one other way we might look at it is positron emission. What's happening here? It's essentially the same thing, but kind of in reverse. Here you've got a oxygen 15, and notice it transmutes to nitrogen 15. So the atomic number doesn't change. But what does change? I said the atomic number doesn't change. The mass number doesn't change. But what does change? Atomic number. And essentially what's happening is the proton is doing what? It's shooting out its positive charge and leaving behind its mass, the neutral part. So a proton becomes a neutron, essentially. And again, here we're seeing that we're starting off with oxygen, it becomes nitrogen, and then that gets shot out as a radioactive particle. It's almost like a positive electron. That's what we're shooting out. That's why it's called a positron. It's a positive electron. Sometimes you may also see that neutrino written in there again. And notice, just like with a beta particle, you may see it written as beta. You may just see E. But either way, this number here has to be positive because we're shooting off a positive charge. Good with that?
What was the difference?
The two of these?
Yeah.
They're not different. The only difference is that they use different symbols. You might see it written as beta, you might see it written as an electron. Just depends on who's writing the question. All right, so here's some sample problems. Let's just fill them in. Here we've got radium, and what kind of decay would this be?
Alpha.
It's alpha. So we add up the numbers. This is 226, and this is 4. Mass number over here has to be 222. This is 88, and that's 2. Atomic number has to be 86. And then we look up in the periodic table, and we find that 86 is radon. All right, so we got potassium 37 here. What's going on in this one? Positron emission. And if it shoots off a positive particle, if this is +1, then this has to be 18. So they add up to be the 19 over here. This is 0. This is 37. That has to be 37. So we look to the table and we find that element 18 is argon.
So a positron has no mass.
I won't say no mass, but negligible mass. It's kind of like an electron. So I mean, we don't even add the masses of the electrons into the weights of atoms, right? So it's very small. Here we've got neptunium, and the neptunium is becoming plutonium. So what's this over here have to be? It's got to be a beta particle. And it's got to be a beta particle because -1 plus 94 is 93. 0 plus 239 is 239. The numbers have to add up. Now over here we haven't looked at the slide about this yet. But what's going on here? We're adding two elements together. We're combining them. That's fusion. And in this case, we just add them up. 1 plus 3, 4. 1 plus 2, 2. And what's element number 2? Helium. That's not really radioactive decay, that's fusion. And the next slide on this PowerPoint's about fusion. We'll get there in a second. Here's another one. This time we've got aluminum 27 reacting with an alpha particle. So we just need to add up the numbers. These add up to be 15. There's 15. This has to be 0. These add up to be 31. That's 30. What's that? It's a neutron. So those two fuse together and then shoot out a neutron. Here's another one. Again, same kind of thing. We're shooting an alpha particle into americium. And notice this means just 2 neutrons, right? So there's 2.
Good old American material.
Yeah, there he goes. Just shoot it out, right? 245, there's 2. So this has to be 243. These add up to be 97. Well, that's 0. So this has to be 97. And then we look up 97. And that's berkelium in the periodic table. Question?
Why is helium the alpha particle chain? Because that's also...
An alpha particle is essentially a helium atom without the electrons, shot at high speeds. So what's happening here? This is probably taking place in like a particle accelerator, and they're literally intentionally shooting this alpha particle at the nucleus of americium, making it happen. It's not something that's probably going to happen very often in nature.
Helium is 1 proton.
Say again?
Helium is 1 proton.
No, helium is 2 protons and 2 neutrons. Right. All right, now right over here on number 7, notice that we're shooting a neutron at something. And then what's happening to that something after we shoot the neutron at it?
It's breaking out.
It's breaking apart. What do we call that? Fission. So we just got to add up the numbers. Over here we've got 142 and 91. That would be what? 233. And then we've got 3 more neutrons, so 236. We've got 1 over here though, so that means it's got to be 235. We've got 56 and 36, which will be 92. 0 over there. This is maybe the most famous atomic reaction that there is. That's the fission of uranium-235, which is responsible for what? Atomic bombs, nuclear power plants. This is the most famous atomic reaction of all time, probably. All right. Filling in these nuclear equations should be easy. Don't make it difficult. Things have to add up on both sides. If you know the symbols and you know that, this is not a problem. All right, a little bit about fission. We know fission means to split. They discovered it in 1939, which was pretty good timing or pretty bad timing, right? Start of World War II. What do those names sound like? Sound kind of German, right? That's would have been bad. Turns out there was also a woman involved, Lisa Meitner, who happened to be, what ethnicity? Jewish. So that was really weird that you had the Germans and the Jews, and she was a German Jew though. But they discovered this reaction, sort of by accident. And what they discovered is when they shot neutrons with like a particle accelerator at uranium-235, that they got barium and krypton. They also got 3 neutrons that were given off. But what's not written in this equation that's the most important thing is they got lots and lots and lots of energy. Okay? Crazy amounts of energy. So they figured that out. Then they started looking at this. This turned out to be real important. Why were those 3 neutrons really, really important? They could go hit 3 more atoms of uranium-235, which could then give off 9 more neutrons, which could go hit 9 more uranium-235, which could give off 27 more neutrons, and just get what we call that? The chain reaction, which could get really big, really fast, and cause chaos or make a whole lot of energy. Either way. Now, they had to have a way to control this. Because number one, if you just did that and let it go out of control, that'd be really bad, right? In a nuclear power plant, they have these rods called control rods. And they slow down or absorb extra neutrons that you don't want to go. So if you want to slow down the reactor, they put in these rods, graphite rods, sometimes they're made out of different things, that absorb the neutrons. What happened in Chernobyl? The nuclear power plant that went bad. They were doing a test, a safety test, ironically. And they pulled out the control rods, at least further than they should have. And then they couldn't get them back in. And the reactor just got hotter and hotter and hotter and hotter and hotter because it was giving off so much energy, and eventually it just exploded. And what happened to all the radioactive materials inside? They got shot up.
Like nuclear exploded or just...
No, it wasn't a nuclear explosion. It was because what makes the power plant work? How does it make electricity?
Steam.
The nuclear stuff is used to heat water, which creates steam, which shoots through what?
Generator.
Yeah, I use the more power plant term. Really. Turbine, which turns a generator, which makes electricity. But so what happened is all this steam built up, and it blew the reactor. The radioactive materials got shot up into the air, went all over the place. The cool thing about it, though, is that most of the people in the town of Chernobyl got out because the stuff shot so high in the air that it took it a long time to come back. And they got out. Most of them were okay. Who are the people who died? the people who tried to clean it up. Some of it landed, around the power plant. Some of it just fell almost straight back down. And so you had this big mass of radioactive materials just open. They couldn't leave it just out in the open because they were afraid it might go fission and it might cause a mushroom cloud kind of effect. Didn't want that. So they tried to cover it up. And somebody had the bright idea of let's just fly over it and drop like concrete over it. What happened to the guys in the planes? Died. Firefighters on the scene didn't know what were going on. Some of them got all kinds of huge radioactive exposures, and they died. And they actually tracked the nuclear waste from this all the way to the United States through the air. Yeah.
Actual benefit of continuing to run nuclear power plants if, like, for instance, what's happening in Japan, like, every week, like, you go online to find out about something happening with some nuclear power plant over there that leaks into the water and then bans fishing. It's just horrible.
Yeah, well, the thing that happened in Japan, there should have never been a nuclear power plant that close to the water. I don't know why they did that. That just wasn't smart. Nuclear power plants, though, are probably the safest power plants overall. And they're cheap. They work well. And are we going to run out of nuclear fuel anytime soon? No. We would probably be better off if we had more nuclear power plants, I would argue. The French, most all their electricity comes from nuclear. And it's kind of ironic, the only place in the world that's ever been nuked, Japan, almost all their electricity comes from nuclear power plants. There's a reason for that. Why does almost all their electricity come from nuclear power plants? They don't have any resources, like natural resources. They don't have oil, coal, and stuff like that. So, in order to keep from having to import all that, they used what was the most efficient method for making electricity, which was nuclear power plants.
We have a nuclear power plant right next to the Lake Gunnersville, right?
Yeah, but you don't have to worry about a tsunami happening in Lake Gunnersville.
That is true.
The ocean is different than a lake. We have 2 nuclear power plants, one on either side of us. Browns Ferry, which is up and working, and there's one in Scottsboro, which they are working on as we speak, and it'll be operational before too long. And we're right in the middle. Yeah. It's I don't know what lake it's in Decatur, near Decatur. So it's near Wheeler Wildlife Refuge. Yeah.
Because I've been up there, right next to the
One other quick thing I'll mention about that. They've got these big cooling towers around the reactor, right?
Yeah.
When were most of these power plants built in the United States? I think it was a little bit later, 60s and 70s. And what were they, those cooling towers, which are there to protect the reactor, what were they designed to take? What kind of hit? The biggest passenger jet around in the 60s. A direct hit, and they were still supposed to be okay. But what's happened since the 60s? Passenger jets are a whole lot bigger. And they're not really sure if, you took what's the new Boeing plane, the huge one?
747.
The Dreamliner. They're not really sure if some crazy terrorist took that plane and rammed it straight into a reactor. They're not really sure what would happen because it wasn't designed for that. So I would argue that probably outside those reactors you're going to find what if you look for anti-aircraft guns. And if the plane started coming, it's probably going to be toast, would be my guess. If we're smart. Last thing I'll mention, and this is the last thing in the PowerPoint. Do I know?
You can argue if we're smart.
Oh, we're definitely not smart. Surely we have that. Fusion. Let me backtrack to fission for just 1 second. There's a lot of people who would argue where Emma was at, that Fission is dangerous. We should stop it. We should get rid of all nuclear weapons. We should close our nuclear power plants. Stop fission. There are a lot of people who would argue that. I don't agree with that argument, but there are a lot of people who would argue. One of the arguments with fission is that, what about these two things, the barium and the krypton, that are made after this is over? They're still radioactive and dangerous. So that's what we would call radioactive waste. And in the United States, where does our waste go from nuclear power
They
plants?
were building a nuclear, but Obama stopped the funding for it, so they can't put it anywhere now.
Right.
They're funded.
We're having a hard time figuring out where to put it. The Bush administration, I think it was Colorado, I may be wrong. So Colorado, some state out west, they basically had a mountain out there that they had burrowed a big chamber into, lined it with concrete and lead and other things, and they were going to take all the nuclear waste from all the power plants in the United States, stick it in Colorado. People in Colorado weren't huge fans of that plan. But the advantage of doing it that way is that it could be guarded. And you could put it in one place, and you could have the military there. And if they got through that, then we got a bigger problem to worry about, right? Now, these things are probably not going to fission. I mean, you're not going to make a nuclear bomb out of these very well. But one thing that I don't understand why terrorists haven't done, because it wouldn't be that hard to do, is to just make a regular bomb and load it up with these things. A dirty bomb, okay? And the scary part about one of those bombs is when it explodes, it's just going to be a regular explosion. It's not going to be a mushroom cloud kind of thing. But all this radioactive stuff gets spread all over the place. Let's say you shot that off in Washington, D.C. What happens to Washington, D.C. for a long, long time? It's evacuated, shut down, too radioactive for people to mess with. And I don't understand why they haven't done that. Because like I said, it wouldn't be that hard to do. There's been all kinds of talk. It may sound like it's a secret. It's been all over all kinds of people talk about it on TV. There's been episodes of different shows with dirty bombs. It wouldn't be that difficult to do. Right, right, that's it. They're just too nice to do it. But fusion. The advantage of fusion, in fusion we're not breaking atoms apart, we're putting them together. And what's the other advantage? You get a lot more energy, number one, and more energy is released. And when it's all over, what do you got left? Helium. Well, we're very concerned about helium being dangerous. Unless you're sucking it out of balloons and you suffocate yourself with it, it's probably not dangerous. But the problem with this is that as far as we know right now, the only way we can make it effectively happen is how? You got to get those things really, really hot. So hot that we don't have anything on Earth that can hold it. That when you put that in a container, the container goes away because it's too hot. We're talking like temperature of the sun hot. They're trying to experiment with doing this with like magnetic fields and lasers to contain it instead of having a physical container, having like a magnetic field or a laser to hold it in. But that's all kind of theoretical right now. There was a Keanu Reeves movie a few years back. I'm trying to remember the name of it. Maybe it was Chain Reaction. It had Morgan Freeman and Keanu Reeves in it. It was a pretty good movie. And they were looking for what they call cold fusion, which is doing fusion how? At like room temperature. If you figure that out one day, remember that we talked about it in this class. Because I want to share the royalties that you get, because Bill Gates will be asking you for money. I'll take just like 0.5%. I don't need much. Small percent. Okay, is all I need. I don't need a lot. But make sure make sure that if you see an equation where you're just adding two elements, first of all, realize it's fusion. It's usually going to be small atoms that they fuse. Usually it's going to be hydrogens. And that typically two hydrogens are going to add up to be helium. Make sure all the numbers add up. If they don't, then tack on whatever you need to tack on there at the end. In this case, it's a neutron. All right, real quick, couple of problems. How many neutrons are in polonium-213? Whatever 213 minus 84 is, right? Walker, what is it? 213 minus 84. 129. According to Walker, it's B. I'm pretty sure it's right. The nitrogen isotope 13, nitrogen 13, listen, emits a beta particle as it decays. So let's draw an equation for that. So we got nitrogen 13 shooting out a beta particle. So now let's just write the equation. We'll finish this one, then we'll be done for today. 13, this is 0, so this has to be 13. 7, this is minus 1, means that has to be 8. Look up element 8, that's oxygen. So it's oxygen 13, which would be C. And that is a good place to stop.
Fusioning physically possible?
But nobody's been able to figure out how to make it happen just yet.
In other words, they're hoping it's possible, but
Probably not.
never.